So, this is lecture 32 and we are discussing non-premixed combustion, so diffusion flames, and primarily we are interested in doing some analysis on laminar non-premixed flames, laminar diffusion flames. And to do such an analysis we need some theoretical tools, and for the time being we are not directly thinking about a particular laminar non-premixed flame. For the time being we will think about just developing some tools, and the first thing that we are looking at is passive scalars and mixture fraction. So, you do not really know what these are. So, it will take some time for us to understand this. Hopefully, today we can make some progress. Remember, towards the end of the class yesterday we defined the chemical system. So, the chemical system is fuel plus oxidizer giving you products, and this set of reactions, and these are the coefficients. Nu primes are on the reactant side, nu double primes are on the product side, but of course it is reversible. So, you have a reversible sign. So, the left hand side is prime, the right hand side is double prime, and you starting with this we can do a mass conservation also. And yesterday I wrote this expression which is in the red box, but this comes from this, which is essentially a mass balance. So, W's are the molecular weights. So, nu prime Kj into Wk is actually the mass of the species, total mass of the species, which are on the left hand side. On the left hand side we write all species, on the right hand side also we write all species. So, this is the mass for the left hand side. Of course, this will be also equal to the mass on the right hand side. Now, this is for j equal to something, some j, but there are multiple j's. So, what are the j's? Do you remember from last class? Different reactions, isn't it? So, there are n species and they are participating in m reactions. So, the subscript corresponding to these reactions are j. So, j goes from 1 to m, and this is how we write the mass balance. Now, we will do a little bit more to define some mass ratios. So, for species K, we have a reaction rate omega dot k, and this omega dot k is summation j equal to 1 to m omega dot k j. Not difficult. So, that means this is omega dot k for the kth species, but the kth species is participating in various reactions. So, you have to add the omega dot k in the first reaction, omega dot k in the second reaction, omega dot k in the third reaction, things like that. So, that is why you have to sum over all j's, and this is also written as a Wk summation j equal to 1 to m nu kj, and this. Now, I do not know exactly what this is called, but we will call it an capital omega. This is the notation which is used in the book Theoretical and Numerical Combustion. So, it kind of looks like this. So, I am writing it the same way it is written in the book. I think it is called a capital omega. So, this capital omega j is omega dot kj divided by Wk nu kj. All right. So, it is just a name given to this, and you can verify if you put this in here, we get this. It is not very complicated, just a matter of new notation. And if we have a single step reaction, if we have a single reaction, then actually we, instead of omega, capital omega j, we can just write this omega because there is just one reaction. So, there is no point in writing j, and then that becomes omega dot k divided by w k nu k, because j is only one, only one reaction that we are talking about. And this gives omega dot k as w k into nu k. So, going back to our basic system, we have fuel, oxidizer and products. So, our omega dot O is this from here, omega dot O for oxidizer, not for oxygen, O for oxidizer. And omega dot F is Wf nu f. So, just borrowing from here, and that means omega dot O divided by omega dot F is Wo nu O divided by Wf nu f. So, you can see the role of this capital omega. Capital omega multiplied by few things will give you omega dot for individual species. This capital omega multiplied by Wo nu O gives you omega dot O. This capital omega when multiplied by Wf nu f gives you omega dot f. Okay, so, that is the advantage. So, you know that if once you have this capital omega, you multiply it by respective species molecular weight and the stoichiometric coefficient. This nu is actually that nu prime minus nu double prime minus nu prime. Okay. So, we can get this. So, this is omega dot O by omega dot f. The capital omega has got cancelled and we call this an S. So, what is this S like? Let us say we have CH4 plus 2O2 giving you CO2 plus 2H2. Can you just mentally calculate this S? CH4 plus 2O2 giving you CO2 plus 2H2. Four, right? Okay, very easy. What I was telling you is that okay, if you do CH4 plus 2O2 giving you CO2 plus 2H2O, then this WO is just 32 molecular weight of oxygen. Mind you, we are writing just oxygen burning CH4, just oxygen oxidizing that CH4. We are not writing air. Okay. So, this WO in that case becomes the molecular weight of oxygen, which is just 32, and then multiplied by this 2. What is this 2? 2 must be that nu O. Okay. So, that will give you 64, and here you have 16 into 1. So, 64 by 16 will give you 4. So, that is S. So, these are all lots of notations, but it is actually pretty simple stuff so far. Okay. Now, what we want to do is write some conservation equations for fuel, oxidizer and temperature. So, there is a conservation equation for fuel mass fraction, conservation equation for oxidizer mass fraction, but there is also a conservation equation for enthalpy from which we can get an equation for temperature. So, I will just write these, and from this you will be able to interpret the terms to some extent. Again, I am writing this without deriving this. I believe that from your previous background of conservation equations through other courses, you will at least be able to make some sense out of this. I actually wrote this equation yesterday for species K, correct? So there is a transient term, there is this advection term, there is a diffusion term, then there is a source term which we called omega dot f. So this is for the fuel mass fraction. So we kind of understand this even though we have not rigorously derived this. Yeah. So this is the fuel mass fraction equation. Then there is an oxidizer mass fraction equation which is given by this, which looks similar to the fuel mass fraction equation, except that this has omega dot f, this has s times omega dot f. That is expected because just a few minutes back we saw that omega dot o should be equal to s times omega dot f, and s is just this ratio. For example, for the CH4 plus 2O2 reaction, s is equal to 4, correct? But we also have this energy equation, and in the energy equation we see that again similar terms. There is a transient term, then there is this term due to velocity here, and then there is a diffusion term, and then there is another source term. So you will notice that the source term has a Q. So the Q has to do with the heat which is released in combustion per unit mass of fuel. Okay. And then you have Cp, and then you have omega dot f. So you will notice that all three equations now have omega dot f. Let us see whether we can develop some more understanding of these equations. So we will look at, actually I think we will do the energy equation. Yeah, should work. This is the energy equation. This is the form. Number 3 is the form in which we want to use this. Number 3 is the form in which we plan to use this for a further derivation. Now, actually for constant pressure flames where the flow field is actually, the flow speed is actually low, and Cp values are all equal, in that case it can be shown that this is our energy equation. For this we can see the book by Poisson and Venant. So this is from the book, or there's another book which is listed in the course introduction sheet, that is a book by Kuo. So all these books can be referred to get this. This is for constant pressure, low speed flames where Cp's have been assumed to be equal. Okay. So what I plan to do is start from here and show you that from this we can get number 3. Okay. That's at least better than directly writing number 3. That's all. But doesn't tell you the whole story, because I'm now assuming this, and then from this we are going to 3. So even that this is not the complete picture. Fine. But we have rho Cp d temperature dt. So are you familiar with this capital D business? You've seen this before? Yeah, so this is a total derivative. So that's one thing that we will remember. We will also remember that we are writing del xi. So xi may be the coordinate directions, x1, x2, x3. Okay, so it can be x, y, and z. Yeah, so this is a body force term. So where this F's are actually body forces, and this term also we are going to neglect. We will not, in our flames we will assume that the effect of body force is not significant. So let's not bother about this too much. This is a body force term, and this will give you the heat diffusion terms, lambda is thermal conductivity. Okay. In equation 3 as well as in here, lambda is thermal conductivity. So, this must be a diffusion term, then there is this omega dot T. So, this must be a source term for energy equation. So, we have this total derivative term on the left hand side, we have the source term for the temperature equation, which is omega dot T. We have terms which show heat diffusion. Okay. How do you know it is heat diffusion? It is because it is like ddx of k dt dx, but instead of k we are writing lambda as a thermal conductivity. As I told you yesterday that we are trying to now stick to the notations used in the book theoretical and numerical combustion. So, this lambda is actually thermal conductivity. We have been using k before, but as of now this is lambda, and this is the body force term which we are going to neglect. So, it is primarily this. In fact, we neglected something else. If there is, let us say, some laser source in the flame region, or maybe some spark in the flame region, or some radiation flux going into the flame region, those sort of things will give you a heat source term. Now, heat source term, by a heat source term I do not mean the thermal energy which is released because of combustion, I do not mean that. Okay. That will come somewhere, of course, that of course has to come through that omega dot T, right. So, there is chemical energy getting converted to thermal energy. So, that term has to be taken into account, otherwise why are we studying combustion. So, that has to be there, but apart from that there may be some spark given in the flow field, or there may be some radiative flux which is coming from outside going into the flame region, some laser being focused into the flame region, things like that, but we are neglecting those. So, we are neglecting heat source terms. So, we could have written another heat source term here which we are neglecting, no external heat source. Not exactly external, what I mean is not non-combustion sort of thing is not included here. Okay. Now, it is actually not a difficult thing to show that rho Cp d temperature dt will be rho Cp this by definition of the total derivative, capital D temperature, capital dt, it is actually the total derivative. Right. So, that is also equal to all right, and we can write this to be we are assuming Cp to be equal and constant, not density. Okay. Now, as I told you a few minutes back, no need to write this down, just have a look at this and see whether this makes sense. This is equal to this is okay, right, definition of the total derivative. From this can we write this?
That rho has to be inside.
Which row?
Rho Cp. So Cp we are taking constant, that's why it is outside. In the total derivative, then only we can write.
Yeah. So that is one response. Let us see whether there is any at all any sense, or what is it all incorrect. This term is same as this, okay, and this term is same as this. So, looks like I have added two terms. So, is that all right? Can that be done? So, I have added these terms in blue. Okay, otherwise it's the same thing as the previous line. So why do we add these two things in blue? We can add these two things in blue if, yes, continuity, mass conservation. So, if you add these two things in blue, then what do you get? Then you get CPT as common. Okay. So, these two are like CPT del rho del t plus del del xi of rho ui, correct? And this is continuity equation, isn't it? So, it is del rho del t plus del del x of rho u plus del del y of rho v plus del del z of rho w, that sort of thing. Okay, so this is continuity equation. So, this is actually a trick to add these two terms, that is all. We added these two terms to play a trick, so that it comes to this form. Now, it can come to this form. So, now you are saying that writing this equal to this is okay, fine. This line and this line are the same. Now, this line and this line are the same, that is easy. Okay. That is definitely easy, because we are clubbing these two together and we are clubbing these two together, correct. Cp has been taken to be constant, by the way. Okay, so you can in your mind you can think of this Cp going in here. So, Cp has been treated as a constant. So, all individual species Cp's are equal, but the Cp value is also constant, meaning it is not dependent on temperature. So, as you will notice that this is something which we are doing for the sake of developing an idealized model of combustion. So, we are making simplifications. If we keep everything variable and if we do not make any assumptions, then we can't really develop a theory which we can handle, fine. That is the whole idea. So, Cp is all equal, Cpk is all equal and treated as a constant. In the derivation that we are actually doing today, we are making some assumptions, like we are taking the thermodynamic pressure to be constant, Mach number to be small, that is low velocities. Then we are taking all diffusion coefficients of individual species to be equal to some overall diffusion coefficient d, and heat capacities, just as I told you now, all heat capacities are taken to be equal, Cp, and the Cp's are also taken to be constant. Later on we will also see that we will assume the Lewis number to be equal to 1. Remember Lewis number, we had seen this some time back. So, that is alpha by d, thermal diffusivity we divide by mass diffusivity, and in this case it will look like lambda by rho Cpd equal to 1. So, that is going to also come sometime later. Alright, so what we have seen just now is that this is okay. This is okay. This part is correct, right? And what else? We will go back to this equation. Remember our objective, we are starting with this equation, we will neglect the body force term. So, then we are left with this and these three terms, and then we will see whether we get equation 3 some time back. We had the set of 3 equations. So, now our energy equation will look like I just dropped out that body force term. And then the remaining questions are, what is this omega dot t? Omega dot t will be written as minus q times omega dot f. We know what is omega dot f. So that has to do with the fuel consumption rate. And multiply that by q. What is q? Q is the heat released due to combustion per unit mass of fuel. Okay. So the relation between these two is this, and this is understandable, right? And the rate of consumption of fuel multiplied by heat released due to consumption of unit mass of fuel must relate to a source term in the energy equation. Okay, because in the energy equation you will not have terms like omega dot f. You will not have what I was writing a few minutes back. This is the set of equations that we are working with. So this has omega dot f, fine, but this is the consumption rate of fuel. Now the source term in the energy equation cannot be exactly with the same dimensions of omega dot f, right? It has to translate to energy, correct? So who is doing the translation? It's actually omega dot f multiplied by q that will make it from a species consumption term to an energy consumption term. But why do we have the negative sign? We have a negative sign here, isn't it? Yeah.
Q dot f was because it is released.
Yeah. Yeah, so omega dot f is probably itself negative. So multiplied by minus q, so that will give you an omega dot t, right, which is positive. So energy is getting released. Now let us be also careful about something. What are the units? Because as I said, you have to be careful and patient, because we now shifted to some other books. So there is new notation. What you should do as a homework is actually check all terms in these three equations for units. Okay. This has to be done, otherwise we will keep getting confused. Let us see, let us do something here. What about this one? What is the unit of this? Yeah, so we can write this as kg per meter cube second. So I will leave it to you to check whether this is also kg per meter cube second. You can also check whether this is kg per meter cube second. Do you think this will be kg per meter cube second? Okay, so del del xi, that means 1 over meter rho kg per meter cubed d meter squared per second, and del yf del xi 1 by meter. Okay, so are we getting kg per meter cube second? Yes, we are getting kg per meter cube second. So this is also kg per meter cube second. So this is tricky, because I think we used previously kilomole per meter cube second for omega dot terms, isn't it, when we are referring to Tanz's book. So you have to be careful. Just forget about Tanz's notations for a while. Okay. So this is kg per meter cube second. And what about so what about the energy equation? What are the units?
All are in heat generated per unit volume.
Yeah. So
Kelvin only.
kg.
kg Kelvin
Hmm.
per meter.
per meter cube.
Okay, it's looking a little odd because we have actually divided by Cp, isn't it? This equation is after division by Cp. So if we look at the units before dividing by Cp, then this term will be just this term will be del T of rho Cpt, isn't it? So that is kg per meter cubed. Cp is
So kilojoule per kg Kelvin.
kilojoule per kg Kelvin, and this is Kelvin. So okay, there is time also.
Kilojoule per meter cube second.
Watt per meter cube.
Kilowatt per meter cubed.
Kilowatt.
So this is power per unit volume. This is what these terms are. It looks a little odd because here it looks a little odd because you have divided by Cp. But it's actually this balance means that you have taken this control volume and you are seeing how much energy per unit time per unit volume you can account for because of various processes. So one process, for example, is the chemical energy release in the flame. So that's why you have Q into omega dot F. Q into omega dot F. Omega dot F is kg per meter cube second, and Q should be kilojoule per kg. Okay, Q is kilojoule per kg because that's energy release per unit mass of fuel. So kilojoule per kg multiplied by omega dot F, which is kg per meter cube second. So that will give you kilowatt per meter cubed. Fine. So this sort of checking is important. Now going back to what we were doing, we are trying to get this number 3, equation number 3. We are trying to get this equation number 3, and we started from something else, right? Some other equation with the total derivative. We started from there, and we have arrived here, and you can already see that we have almost got number 3. Okay, so what do you have to do now? You just have to divide by Cp. That's okay. If you divide by Cp, because we are taking Cp to be constant, then this equation will give del T of rho T. Let's write the diffusion term first. Omega dot T is minus q omega dot f. So this is minus q by Cp omega dot f. Okay. So this is your 3, in fact. This is your 3. This is the same as 3. So through this small exercise, I have shown you that you can start from this equation, which is somewhat more general. This is still for constant pressure, low speed situations, and equal values of Cp. So from this you can start, you can integrate, you can build in the continuity equation, the mass conservation equation, and arrive at another form of energy equation, which actually is nothing but our number 3. Okay. So all these now, I think, at least in a broad sense, is something which I believe you will physically understand. All equations have similar kind of terms. I told you about the species equations. Energy equation also, there is a transient term, then there is energy transport because of velocities, and there is this diffusion term, and then there is also the source term. Okay. Now let's think about it. Do we have all the equations? Yes, actually in a sense we have, because even though mass conservation is not directly shown, it is in fact included. Now, if you are asked to solve a diffusion flame problem, remember this problem of a tube and this fuel coming out through this tube out to an oxidizer field which is infinite and quiescent. So suppose you are given that kind of a problem. If you are asked to solve this, what will you do? You have to set up equations. And what are the equations that we have? We have mass, momentum, and species and energy. If it was just air coming into air, then there would not have been any need of using species equation. But we are doing combustion, so we always have species equations. So because it's combustion, we have species equations in addition to mass, momentum, and energy equation. So we have got all these equations in front of us, right? Now, our purpose will be to try and solve them and get all the profiles. Remember our objectives that I told you yesterday. We are trying to solve this diffusion flame problem to see how temperature varies with spatial coordinate, velocities vary with spatial coordinate, how mass fractions vary with spatial coordinates. Okay? And from all those we wanted to get the flame height and the flame shape. Okay? So this can actually take you closer to that. But I also told you that right now we are not going to do a solution of all this. Right now we are just going to see what is the concept of passive scalar and what is the concept of mixture fraction. So we are trying to define few things which will make our solution of equations easier. Fine. So that in that context we have developed these equations, and if you look at these equations will tell you something. These equations will tell you that if you use some combinations, okay, of if you use a combination of two equations, for example, if you multiply number 1 by s and then subtract 2 from number 1 multiplied by s, okay, you will get an equation which will not have a source term. Okay. Easy. First equation multiplied by s all through, and then you subtract second equation from that equation. You will not get a source term. Okay. So we will do things like that, and that has a significance. So this is the equation that we have, right. The source terms have dropped out, and we will give it a name. This SYF minus YO, we will call this Z1. Oh, yeah, Z1. Now this is a capital Z, and unlike the way I usually write, see, I usually write Z like this, crossing the middle. Here I will not do this because I want to save that crossing the middle for something else. So this is that just Z1, capital Z1, and this means we got so this is a nice equation which we got for this variable which we call capital Z1, which is SYF minus YO. So this is a linear combination of two mass fractions. Okay, linear combination of two mass fractions. S is a simple thing, like we calculated S equal to 4 for the reaction CH4 plus 2O2. Any other hydrocarbon given to you, we can always calculate S. So S is a simple thing. Now this equation is special because this doesn't have a source term. Okay. Now source term actually makes solution of equations more difficult, because if you think about the YF equation or the YO equation, they have this omega dot F and omega dot O, right? And omega dot F is likely to be complicated. What does omega dot F depend on? It will depend on the temperature, it will depend on the local temperature, it will depend on also the concentrations of fuel and oxidizer. Okay. So this, if you follow an Arrhenius model, then it will have concentration, two concentrations raised to some power, and then also this energy factor which we said exponential of minus E over R bar T. Okay, so all that is going to come, and in fact it's that exponential term is highly nonlinear in temperature. So if you can play a trick and if you can get rid of that source term somehow, then the reaction becomes little easier to solve. That's why we have done all this. So this Z1 is actually a passive scalar. Okay, Z is a passive or conserved scalar. So Z1 is a passive or conserved scalar. Why? Because it doesn't have a source term. So what is Z doing? Z is just moving because of convection and diffusion. It's getting distributed because of convection and diffusion. Because you have convection here and you've got diffusion here, that's all Z is doing. But Z is not getting consumed or generated in some kind of a source term. So that's why it is passive. That's why it is conserved. You can't say the same thing about fuel mass fraction, because the fuel mass fraction equation that we just now saw has an omega dot F, so that there is a source term effect. So it's not just convection and diffusion. Here it's just convection and diffusion. Of course, there is a transient term also. So this is why it's called a passive scalar. And in addition to all this, we'll think about also of other combinations. We just saw, coming back to our number 1, number 2, number 3, we just saw that 1 and 2 could be combined to get a Z1 which became a passive scalar. But looking at this set of 3 equations, you understand that other combinations are possible also, which can give you more conserved scalars. So the other conserved scalars that we can think of are the following. We can have, maybe I can just write this down and you can verify this yourself. Very easy to do that. Okay, so the question here is that what is the meaning of passive scalar? Yeah, so this equation is fine for that. We'll look at this. So here we have this Z1, and what is Z1? Z1 is SYF minus Y oxidizer. So why is it passive? It is passive because unlike YF or YO, the Z1 equation doesn't have a source term, doesn't have a source of sink. So all that Z1 is doing is moving from one place to another because of the effects of convection and diffusion. It's not getting destroyed, it's not getting consumed because it doesn't have a source term. Okay, so it's passive in that sense. So that's why it's called a passive, or as I have written in brackets, conserved scalar. It's conserved because it doesn't have a source term. Okay, there's no destruction, no consumption, not like that. Okay, so what I was telling you a few minutes back is that we can now have other combinations which are possible. So these 1, 2, 3. What we have here, 1, 2, 3, right, 1, 2 and 3. These are all the equations that we have. Okay. Why are we not writing the product mass fraction equation? We could have written that also, but why don't we write it? We just wrote fuel and oxidizer, but our chemical reaction, the broad scheme of things is that there is fuel and oxidizer combining to give you products. So why are we excluding products?
Product will be combination of fuel and oxidizer.
So if we get YAF and Y oxidizer, yeah, because the sum of the mass fractions is equal to 1 anywhere in the domain. Anywhere in the domain. You take your probe and measure anywhere within the flame, outside the flame, whatever it is, all mass fractions have to add to 1. There is no other option. Right? So if you get fuel and oxidizer mass fractions, you can get the product mass fraction. Anyway, that was an aside. What I was telling you is that you have these 3 equations, and we combined 1 and 2 in a way that we got a conserved scalar. Are there other combinations possible? So there are other combinations possible, and I would like you to check that at home, not here. So we'll have a Z2, which is this combination will work, and we'll also have a Z3. Mind you, don't cross the middle, okay, of the Z, middle part of Z. So just write it the way I am writing. So there is a Z2, there is a Z3. These are also conserved scalars, because all these conserved scalars will satisfy Z1, Z2, Z2, Z3 will satisfy okay. So they are all conserved scalars because they do not have a source term. So they just move about because of diffusion and convection. So they are passive. And Z1 is a combination, linear combination of fuel and oxidizer mass fractions. Z2 is a combination of temperature and fuel mass fraction. Z3 is a combination of temperature and oxidizer mass fraction. Okay. And very quickly, actually I will repeat part of this in the next class also. Very quickly, we can in fact construct something else. We can construct a small Z. So now this is no longer a capital Z. So this is a small z, which is so what is Zj, the small zj? This is a new quantity that we are defining. And this is some kind of a combination of z itself and its values in the oxidizer stream and in the fuel stream. So this is O, not 0. Okay. So this is O, English alphabet O, and this is F for fuel. So this is the value of Z in the oxidizer stream. This is the value of Z in the fuel stream. Which Z are we talking about? we have 3 z's, right? We just now saw that we have 3 z's, 3 kind of conserved scalar, passive scalars, which we call z1, z2, z3. So, according to the expression that I have here, small z can also be for 1, 2 and 3. So, there can be a small z1 and there can be a small z2 and there can be a small z3. Okay. So, we'll very quickly we will just do a small z1. Okay. So, what is our capital Z1? It is S times YF minus YO. So, is this correct? So, this is Z1, right? This one is Z1 and this is the value of Z1 in the oxidizer stream. This is value of Z1 in the oxidizer stream. So, this is okay. Why do we have a 0 here? YF is 0 in the oxidizer stream. And what is the value of YO in the oxidizer stream? Some baseline value, YO naught. Okay. And below we have Z1 in the fuel stream. Z1 in the fuel stream will be this, and this 0 is because the fuel stream does not have oxidizer, correct. So, similarly you can analyze this one. This is Z, this is the same as this term. This term and this term are the same, these two are the same. So, you can see that this is a Z. So, this is also called a mixture fraction. Okay, this Z is also called a mixture fraction, and today we are running out of time, but what we will do in the next class is we can easily show that the small z1, small z2, small z3 are all same. Okay. How do you get small z1? From using capital Z1, this relation. In this relation, if you use capital Z1, you get small z1. In this relation, if you use capital Z2, you get small z2, like that. So, if you get Z1, Z2 and Z3, I will show you in the next class that these are all equal. It is possible to show that, and each one of them can be called a Z, and this Z is in fact a mixture fraction. Okay. But that will come later. We will stop here for today. Thank you.